Okay, so let me solve the problem for you. So I hope that you could solve the problem yourself. Here, this is an example. So if you remember last time we talked about long division method and things like that, we want to continue and finalize the lesson that we started last time. So remembering how to do the long division is actually crucial for this lesson. And can you hear me properly? Yes?
Yes.
Okay, good. Okay, so what I'm supposed to do, the claim in the problem is that x squared plus 1 is supposed to be a factor of this. So if I say that, okay, show me that number 2 is a factor of 6, one way to do that is to divide 6 by 2 and show that the remainder is 0. Yes? For example, we know that 2 is not a factor of 7. Why is that? Because if I do the division of 7 by 2, I will get 2 times 3. The quotient would be 3 in this case, but it is not enough. I have a remainder which is not equal to 0. So that is the reason that why 2 is not a factor of 7, but it is a factor of 6. And that's the same idea here. I want to show to you that this is going to be a factor of this polynomial. Last time we learned how to divide polynomials, so it means that, okay, I divide this polynomial according to the algorithm by this polynomial and show that the remainder is 0. Okay, so that is essentially the long division exercise here. Okay, so do you remember, if you want to do this, you write your polynomial and you need to respect to arrange them. If it is not already arranged, you need to write from the highest exponent to the lowest exponent. If it is not already like that, you have to rearrange so that it becomes like this. And then I would do this. Yes, and then you remember you draw a horizontal line up there, a vertical line, for example, here, and then you have another horizontal line here, and then here you put your divisor, which is supposed to be proven to be a divisor. Okay, so do you remember? You can do it in your head. You just concentrate on the first term and the first term and then divide it in your head. 3x to the 4 divided by x squared is 3x squared, and then you put it here. So this becomes 3x squared, and that is your first term. And what you are supposed to do, you take this one and multiply to the whole polynomial here and write the answer here, but you need to be careful. You change the signs from positive to negative, from negative to positive. Yes? So if I do that, this becomes minus 3x to the 4. The next one becomes positive 3x squared, but when I want to write it here, it becomes negative 3x squared. And I start adding these polynomials. So when I add, you see this negative 1 and this positive 1 are gone, but this 2 minus 2x cubed is alone. This cannot be added directly to this one, but this can be added to this one. But I have to respect the order. So I have to bring minus 2x cubed first, and then I add these two. Minus 3x squared plus 2x squared is minus x squared. Then I will bring minus 2x and minus 1 down. And I repeat the process. If you learn this, everything coming after is just a repetition of this idea. Okay, so I do that again. Minus 2x cubed divided by x squared becomes minus 2x. I put minus 2x here. And then I multiply it. Yes, if I multiply it, it becomes minus 2x cubed, but I'm supposed to change the sign, so it becomes positive. The other one also becomes positive. Yes, and then add them again. So when I add them, this one and this one are gone. In this case, coincidentally, these two are also canceled. So what is left for me is just minus x squared minus 1. And I repeat the process. I take the first term, and I take the first term, I divide them, it becomes negative 1, I put negative 1 here, and then I multiply it and change the sign. So it becomes positive x squared positive 1, and as it claimed in the problem, you see the remainder is 0. So because the remainder is 0, this means that x squared plus 1 is a factor of a p of x. But now, the rest of the problem asks you to solve the equation p of x equals to 0. So you see, if I haven't given you this extra piece of information, if you remember from the motivation from the last session, it is not easy at all to factorize this on your own. Yes? But now that I have an extra piece of information regarding my polynomial, I divide it, I get the remainder 0, then I can say my polynomial is equal to the divisor multiplied by the quotient plus the remainder. But because the remainder is 0, if I write this, this gives rise to the factoring of my polynomial. So I would say that hence what we can write, we can say that p of x is equal to x squared plus 1 multiplied by the quotient. And then in principle, I should write plus the remainder, but the remainder is 0. We don't write it. And this is the only one. This is the only remainder that will work. Assume that you get a remainder equal to 1. Then I put 1 here. This is useless. This is a correct equality. This is true, but useless for my purpose. Because if I put this in this form equal to 0, I cannot solve it. I want to have 0, but if I move 1 to the other side, it becomes -1, and the product of two numbers is equal to -1. I cannot draw any specific conclusion out of it. So it is important. I want you to understand these things. Okay, then I am supposed to solve p of x equals to 0. So it gives rise to this, either this one is equal to 0 or the other one is equal to 0. And I am supposed to solve this equation on the set of complex numbers. Hopefully, you don't need to spend some time on it. The answer from here is what? Plus or minus I. Yeah, so that is two possible answers coming out from here. And then I have to use, for example, ABC formula to solve this problem as well. Yes? So let me just do that. That is up to you. It's very simple, so let me skip that. If you just do ABC formula for this problem, what you will get at the end is 1, yes, and the other one is minus a third. So this equation has 4 solutions. 2 of them are real, 1 and minus a third, and 2 of them are complex, plus and minus the imaginary unit. Okay, any questions so far? Good. Now, there is an important theorem here, because this is also usual in these kinds of questions. I told you that here you usually are provided with an extra piece of information. For example, this was an extra piece of information in this problem. And if you go back here, you see on the first part, I am asking you to show that x equals to 2 is a root. Then this is an extra piece of information provided for you. Using that fact, you can solve the problem. Sometimes they can ask you to solve this equation without providing you an extra piece of information. Actually, if this happens, this is not always the case, but if this happens, they are using this theorem, even though they haven't mentioned it explicitly. But because I don't want you to just memorize things, I want you to see why that's correct. So this is why I'm putting it in the form of a theorem, which is easy to understand, and then we use it freely. So assume that you have a polynomial of this type, but there is an extremely important condition that I am imposing on my polynomial, and these are the coefficients. The coefficients are these numbers that you see here. I am demanding that all these coefficients are integers. Okay? Now, if x node is an integer root of this polynomial, x node divides, we had it in Math 5, yes, divides a node. It means a node should be divisible by x node, or X node is a divisor of A node. Okay, you might say that why this is useful. First of all, this is useful. You see, all the polynomials that I was teaching you about, you see, if you look at these coefficients, all these coefficients are integers. So I don't know, you see, all coefficients are integers. So that is actually an important part of this lesson, that I haven't seen even one single question that they are giving you polynomials with non-actually integer coefficients. So first of all, this is not that limitation for our purpose here today, because mainly we are dealing with polynomials whose coefficients are integers, whole numbers, yes? Now, this is claiming that if this polynomial has an integer root, that integer root should be a factor of the constant term. Let us see why this is correct. You can consider it as a problem in Math 5 and number theory, but it is very, very simple. So let us check. What does it mean? You tell me that X node is a root of P of X. Then from this sentence, I can conclude that P of X node is 0. So it means that if I replace X with the given proposed root, the answer should be 0. This is the meaning of being a root. Yes? And then what is the meaning of P of X node? It means that go to your function, in this case your polynomial, wherever you see X, take them out and put X node instead. Okay, so that's the meaning of P of X node, yes? So this means I have A sub n X node to power n plus A sub n minus 1 X node to power n plus 1, and then I continue plus A sub 2 X squared plus, X node squared, A sub 1 X node plus A node is equal to 0. Okay, so now what I do, I keep this one on the left-hand side and I move everything here to the right-hand side. So let us see why this is useful. This gives me that A node is equal to minus A n X node to the n minus A sub n minus 1 X node to the n minus 1 minus up to minus A sub 2 X node to power 2 minus A1 X node. Okay, and then what I can do, immediately I see on the right hand side, all of them share this factor of X node, so it means that I can factor it out, yes? So I will get X node and minus A n X node to power n minus 1. The next one would be A sub n minus 1, X node to power n minus 2, and I continue. This one becomes A2 X node, and the last one becomes A1. Now my question for you, don't let this distract you, but can you tell me what type of number is this number? It's an integer, yes. Why? Because from the beginning, I told you that the coefficients are integer, and now we know that X node is also an integer. So hopefully you agree that this combination is an integer. So I would say that this expression is an integer, so it belongs to the set of integers. So let me call it Q. So then I would say that A node is equal to X node multiplied by Q, where I'm calling it Q, okay? So I'm giving it a name Q. So where Q belongs to Z, okay? But what is the meaning of this expression? Do you remember in Math 5? You don't need actually even remember that. So it means that X node multiplied by an integer is equal to A node. It means that A node is divisible by X node. Or, in other words, X node is a factor of A node. Okay, so this means that X node divides A node. Okay, This is for those people who are interested to know why this is indeed the case. But be careful, this is not claiming that if X node is a factor of A node, it is necessarily a root. No, this tells you that if X node is an integer and is a root, then that root should be among the divisors of A node. Okay? So let me go back here. So let me read this remark for you. The above theorem implies that if a polynomial with integer coefficients is supposed to have an integer root, that integer root should be among the divisors of the constant term of the polynomial. In other words, if none of the divisors of the constant term of a polynomial with integer coefficients is a root, if none of them is a root, then one can conclude that the polynomial does not have any integer roots. So let us see how this might help us. So you see, this is the first time I am asking you to solve a higher degree equation, an equation with degree higher than 2, here in this case 3, and I am not providing you any extra piece of information. Usually, if this happens in the course questions in the book or exam or whatever, it means that there might be an integer root, so you can you can test your chances of how lucky you are. But you need to know where to look for. If I am saying that if this polynomial is supposed to have an integer root, that root should be among the divisors of the constant term. Okay, so it means that a very good candidate for the integer root of this polynomial, we know at least where to look for. There is no guarantee that where we are looking for, we are finding a root. But if this polynomial is going to have an integer root, we know where to look for. We are not lost. That is the main point of the previous theorem. So what we do, we say that let me list the divisors, the integer divisors of 2. What are they? Integer divisors. So I would say, of course, divisor is more or less always integer, but let me emphasize that. Integer divisors of the constant term 2. So what are they in my list? One of them is -1, the other one is 1. The numbers that 2 are divisible by. The other one is -2, the other one is 2. So I do not have any other number as the divisor of 2. Yes, if you don't understand something, please let me know, because I cannot see anything. I'm completely disconnected from you. I'm just concentrating on my iPad. So you can just speak a little bit louder if you want to have any questions. Okay, but then unfortunately, of course, the situation is not very bad. There are only 4 numbers. I don't know. I will start in order. I will start checking them one by one. If I am fortunate, if I am lucky to get one of these things work, then I know what to do. Then I will be in the same situation that I was before. In those problems, the extra piece of information was directly provided for me, but now I am just investigating, I'm exploring to find one. But according to the previous theorem, at least I know where to look for, not just randomly doing things. Yes? So, for example, I check -1. Let us see. -1 to power 3 plus 3 times -1 to power 2 plus 3 times -1 and then plus 2. Yes? Is it 0? It becomes -1 plus 3 minus 3 plus 2. Yes, it becomes a 1, so it is not 0. So, okay, so I cross it over. This is not correct. Let us check the other one, 1. So it becomes 1 to the 3 plus 3, 1 to the 2 plus 3 times 1 plus 2. So definitely, by the way, I really don't need to waste time, because every sign is positive. It is clear that this cannot be the answer and that cannot be the answer. So that was my bad. I don't even need to check. Yes, because everything is positive here. It is completely clear if I put 2 here, it will not work. It becomes positive. If I put 1 here, it becomes positive. So let me just cross them over. So I only have the hope for this one. Let us test this one. If I put minus 2 there, it becomes minus 8. So let me write minus 2 to the power of 3 plus 3 times minus 2 to the power of 2, 3 times minus 2 plus 2. Let us check. It becomes minus 8 plus 12 minus 6 plus 2. Is that right? Yes. It becomes 0. So it means that by inspection, I realize that minus 2 is a root. Then I am in the same situation. Okay? So what I have to do, I have to divide this. So let me start from here, small. I was a little bit careless about my spacing. So let me move it a little bit here. Okay, now I know what to do. I go here and I will write x to the 3 plus 3x to the 2 plus 3x plus 2, and I divide this expression by, can you tell me what? X plus 2, thank you, because I realized that minus 2 is a root, so it means that x minus minus 2, which is x positive 2, it is a factor. Okay, so let us just do it quickly. So I put an x squared here, and then I add them. The next one is positive x. The next one is positive 1. Okay, as predicted. And then, of course, this equation, therefore, the equation is what? We have x plus 2 multiplied by x squared plus x plus 1 equals to 0. Of course, this gives one of the answers that I'm already aware of. So it becomes minus 2. So that's not a big surprise. And then I need to solve that equation. I use ABC formula. So it's minus 1 plus or minus square root of 1 minus 4 divided by 2. But 1 minus 4 is a square root of... So let me write it. You know these things. Let me just skip explanation all the time. So this is also another pair of solutions. So 2 of them are complex and 1 of them is real. Okay. That is another theorem that I want to mention it out. It's another important theorem. So let P of z be a polynomial with real, not integer, real coefficients. You might say that all the integers are, all the coefficients should be real. I would say no, because we are working in the chapter of complex numbers. If you remember, I had given you some examples of equations for which the coefficients were actually complex numbers. So this theorem doesn't deal with those kinds of polynomials. It only deals with polynomials with real coefficients. Now, if the complex number z node is a root of this polynomial, then its conjugate z node bar is also a root of P of z. Okay? So I can prove it in its full generality, but then it takes a long time to write things down. Let us consider that this polynomial, you can immediately realize what I am saying for this polynomial of degree 2 can immediately be modified to include all the general situations, yes? So yeah, I just want to give you the ideas, but because the ideas are the same. So for example, assume that my P of z, okay, is just a polynomial of second degree. So I would write it as az squared plus bz plus c. Yes, you immediately realize that what I am saying now will be immediately modified to any degree polynomial. Okay, what we know that a, b, and c are real. Okay, can you tell me what happens for A bar? If A is real, what is A bar? Can you tell me? No, if A is real, for example, what is the conjugate to 1? What is the conjugate to 2? So what was the conjugate? Do you remember? If Z is equal to A plus BI, if I ask you what is the conjugate, you keep the real part as it is, you change the sign of the imaginary part, it becomes the same thing. Okay? So what happens if I have a real number? It becomes itself. So that is the crucial part. So A bar becomes itself, B bar becomes itself, and C bar also becomes itself. And do you remember we had different rules? We know that if I have two complex numbers added and then I want to take the bar, do you remember? It is possible to put the bar here and the bar here. And then we learned that if I have ZW bar, it becomes Z bar W bar. And we also learned that if I have Z to power to an integer power, if I want to take the bar, I can take the bar from the number and then raise it to power 2. Yes, so yeah, I should have written them actually in a different color. So let me take it here and change the color, for example, to purple, and then yeah, I can put this in a box. This is one of the things that we studied, and I told you that this is actually important to know. Hopefully it will work. Yes. Okay. Now you are telling me that Z node is a root. Yes. So what can I conclude? I can conclude that P node. So do you have something to say, Christine? But I am in this. I checked this aula. That one is also occupied. Yeah. Yeah. Thank you very much. Thank you. Sorry for that. But because I checked the schedule, I don't know what happened. Yeah. Yeah. Thank you very much. Okay. So P of Z. So P of Z node is equal to 0. So what does it mean? It means that A Z node squared plus B Z node plus C is equal to 0. If two complex numbers are the same, do you agree that I can conclude that the conjugates are also the same? So the conjugate of this is equal to the conjugate of 0. But here I can break this conjugate to all of them, break down it to 3 pieces. You see, let me write it one step. So it means that I can write it as this one squared and the other one, sorry, AZ squared bar, BZ bar, and C bar, but no one writes 0 bar because 0 bar and Z are the same. Okay, let me just do one more step. It becomes A bar Z node to the power of 2 bar plus B node Z node bar plus C bar is equal to 0. And the last step, you see here I use this rule. I was able to break this 1 bar into 3 bars. Here and here, I am using this rule. I was able to break down 1 bar on the product into 2 bars, and the same here. Now I want to use the last one. I want to move this bar on top of Z node, yes? So this becomes A bar Z node bar squared plus B bar Z node bar plus C bar is equal to 0. And now I am relieved, if instead of A bar, I can write A. This is now you understand why this assumption was crucial here, you will see. It becomes A Z bar node squared plus B, for the same reason B bar is equal to B itself. Okay, so hopefully you are with me up to here. Okay, and now you see that there is nothing specific about the second degree. If I have third degree, I will do exactly the same thing. I will get this here. Can you tell me what is the meaning of this? If I ask you, what can I write in a more compact form instead of this? What do you tell? Compare it, compare this one. Yes, P of Z node bar, thank you. P of Z node bar is equal to 0. What does this mean? This means that Z bar is a root. Z node bar is a root. Yes, is a root of P. And then where I started with, I started from this assumption that you told me Z node is a root. I ended up with Z node bar is a root. So that's an extremely important problem. You might say, how can I use it in practice? I will teach you now how to use it. At least know the theorem. The theorem tells you that if you have a polynomial with real coefficients, and for some reason, somehow you know that a complex number is a root of your polynomial, at least you know one more immediately. You know the conjugate is also a root. That's extremely important. Let us see how this theorem will serve us in practice. Okay, so I have taken this problem. That was a nice problem from this Matematik 5000 volume 4. So there are 3 problems there. I realize that they are very nice problems, so let us start solving them. So you see here, let me see how much space. Yes, okay, I predicted probably correctly. So consider the polynomial this. You see, first of all, what are the coefficients? The coefficients are all integers, so it means that the coefficients are all real. This is important for our case here. Again, it has given you an extra piece of information. But just with this extra piece of information, I will show you, you will be in trouble. I will try to motivate you why you will be in trouble even if you are having an extra piece of information here. First of all, let me just divide them. Let me try to write small. Okay, so this part is easy. It is asking you to show that I is a root of this. Okay, so let me just do that. What I have to do, I have to, I have to put I there. So it becomes I to the 4. So let me write the left-hand side is equal to I to the 4 plus 2I to the 3 plus 3I squared plus 2I plus 2. Now, if I ask you what is I4, I hope that you remember these things, so it becomes 1, but what is I3? It is minus I. What is I squared is minus 1. What is I is just I, and what is 2 is just 2. You see, this 2I and that minus 2I are cancelled. 2 minus 3 and 1 are also cancelled, so this is equal to 0. So this is equal to the right-hand side. Yes? Okay, so this is good. But assume that you don't want to use the previous theorem. You might say to yourself that, okay, I have one piece of information here, and then so I can use the previous trick to solve the problem. Can you predict, can you foresee what is the problem here if you just want to start immediately? No, that's not a problem. Of course, it becomes a little bit harder problem. This was a level 3 problem in that Mathematics 5000 book. But can you foresee what will be your problem? So usually, let me just make it more clear. Usually, you might be in a hurry and just write this. I'm not saying this is wrong, but I just want to see why you will face trouble a little bit later. I should divide it by what? Can you tell me? If assume that you want to follow the same method that you have learned so far, and you know that I is a root, so usually you say that why not? Let me start the old trick. So what is the old trick? You write this and divide it by what? Can you tell me? not x here, z minus I. Okay, you might say that, okay, this problem is new to me because I haven't divided by a complex polynomial. You are right, but I don't think you will face a big problem here. But can you tell me why this is not that efficient, especially for the second one that I want to solve the equation? Can you predict what is going to happen if I just start doing it right now? Yes. Elaborate more a little bit. Exactly, exactly. So it means that if I divide this by first degree polynomial, because the degree here is 4, what will be coming in my quotient? It would be a third degree. Then what do I have? I will have z minus I multiplied by a third degree polynomial. Yes, third degree. And then, of course, equals to 0. Either this one is 0, which is not very useful because I already know about it. And then I will have the third degree polynomial equal to 0 again. But then I am in the same situation without extra piece of information again. Because a third degree polynomial is also not simple for me to do. I need to have an extra piece of information for that. Might be I can use the previous trick again, but assume that all the coefficients, all the roots are going to be complex. Then the previous theorem will not be able to help. So I want you to see that what is the main problem, why the previous method is not very useful in this case, even though it's correct. The reason is that after division, you get a third degree polynomial. And then if you want to use the zero product rule, then you will face the same, more or less the same problem. Of course, your problem is simpler because you were able to reduce a fourth degree equation to a third degree equation. I would call it a step forward. But it is not complete yet because even third degree polynomials is hard for us to calculate. So I hope that you understand what is the downside of this method of doing that. Of course, let us see how time will serve us. So I want you to be able to do it by complex division by complex numbers as well. Okay, but this let us, for example, let us just start the new method. How can you tell me how the previous theorem, just this theorem, can help me might be solve this problem easier? This theorem tells you that if you know that a complex number is a root of your polynomial with real coefficients, its complex conjugate is definitely a root. So I would say that because this polynomial has real coefficients and this is a complex number, if I use the previous theorem, this is not one piece of information. It is two pieces of information. Yes, one root is I, definitely another root is immediately known to us. What is the other root? Can you tell me immediately? It's minus I, because the conjugate of I is minus I. Okay, so you see, I is a root. So let me write this in all the details here. I is a root. Okay, so if you don't mind, let me, yeah, okay, the name is PZ. So it means that this implies that Z minus I is a factor of P of Z. But now, from here, you can conclude something else. Previous theorem. This implies that I bar is also a root, is a root. So this means that Z minus I, which is Z plus I, is a factor, is also a factor of P of Z. Okay, now I would say that Z minus I is a factor and Z plus I is a factor, This means that P of Z is divisible by Z minus I times Z plus I. Is this implication clear for everyone? When you say that Z minus I is a factor, it means that P of Z is divisible by this. For the same reason, P of Z is divisible by Z plus I. But these two doesn't have any factor in common. It's exactly like this situation. If a number is divisible by 2, it is also divisible by 3 at the same time. I can conclude that my number is divisible by the product, which is 6. Yes? This works because 2 and 3 doesn't have any factors in common except 1. But if I say that I have a number x which is divisible by 4 and it is divisible by 6, can I conclude that x is divisible by the product 24? The answer is no, because when you say that x is divisible by 4 and 6, it might be 12, for example. 12 is divisible by 4, it's also divisible by 6, but it is clear it's not divisible by 24. The reason that you face this mess here is because there is an extra factor in common between 4 and 6, and that factor is 2. But for the case of 2 and 3, this always works because 2 and 3 doesn't have anything in common, any factors in common. And that's exactly the same thing. Z minus I, it is the only factor of itself. If I ask you what are the factors of Z minus I, you would say plus or minus 1, and Z minus I itself, or any plus or minus 1 of this one. So the same thing for Z plus I. So this is a crucial point. If a polynomial is divisible by 2 other polynomials, and these two polynomials doesn't have any factor in common, you can immediately conclude that the polynomial is divisible by the product. But what is a better name for the product? The better name for the product, that's the conjugate pattern. It becomes the first one to the 2 minus the second one to the 2, so it becomes z squared plus 1. Now you see that how this solves my problem. I want you to see this example is a very nice example of the application of the previous theorem. Yes? So now I know that, you see, I had a fourth degree polynomial. In the problem, they gave that I is a root. Because of the previous theorem, I realized that its conjugate is also a root. So, and then because of this argument here, I realized that my polynomial is not only divisible just by z minus I can say more. It is divisible by z squared plus 1. But then, if I divide by z squared plus 1, I will not face the same problem, because this is a fourth degree polynomial. If I divide it by the second degree polynomial, the quotient becomes a second degree polynomial. And that is very easy to solve again. I will not face the previous problem. Okay? I hope that you understand what is the problem here. Okay? What I will do it now for you. So the rest of it is actually just repetition. You know what to do, yes? So you just write z to the 4 plus 2z to the 3 plus 3z squared plus 2z plus 2, and I divide it by what I got here, yes? Z squared plus 1. So, okay, now let me make it bigger. And if you don't mind, I always am a little bit careless, so let me just move it here. Okay, so now I just do the division quickly. So because this is something you already know, so I put z squared here. It becomes minus z to the 4 minus z squared, and then I add them. So this one and that one are gone, and then I will get 2z cubed plus 2z squared plus 2z plus 2. I divide one more time, it becomes 2z. I multiply it here, minus 2z cubed minus 2z. And when I add them, there are two terms that are cancelled. One of them is this one, the other one is that one. And then I get 2z squared plus 2. And then I divide it by z squared, it becomes 2. Comes 2. Yes? And now, so P, therefore, what can I conclude? P of Z is equal to Z squared plus 1, and then I have Z squared plus 2Z plus 2, yes? And then when I put P of Z equals to 0, this gives me that Z is equal to plus or minus I, which is not surprising. I knew about this before. And then the second one is doable now. You see, I don't need to do everything from scratch again. So this is a quadratic equation. I know how to solve it, yes? So what can I conclude? I would say that Z is equal minus 2 plus or minus square root of 4 minus 8 is minus 4 divided by 2, and then you have to write it in the correct form. So it becomes minus 1 plus or minus I. So these are other two roots, yes? Is that understandable? So you see how this theorem helps us to. There is one type of this problem, level 2 problem, in your book as well. Okay? So if you don't want to use this idea, then you would be in trouble. Okay, but here, I just for practice, I want you to be able to do it. I want you to be able to divide this by Z minus I as well, even though this problem is finalized. So what I'm doing, I am just giving you an extra piece of exercise. Yes, because in the first part, we realized that I is a root. According to the piece of information, I know that this should be divisible by this. This is the first time that you are facing, if you want to, of course, this is the real solution. But if you want to do it, you need to know how to do it. So let us just do it for practice. So let me change my color here. So I want you to learn how to do this. Z to the 4 plus 2Z to the 3 plus 3Z squared plus 2Z plus 2. And then I don't know if I have enough space here. Hopefully. So I would write Z minus I here. Okay, so let me write as small as possible here. So, okay, so let me just do it. I take Z4. This is a little bit tricky. Let me see if I have enough space here. No. Okay, so let me just do that because I can take this with me. Cut. And let me add a page here. The page after. The current template. So here. Okay. Okay, now we have enough space to do this problem. Okay, so how should I do that? That was not a good place here. Let me just keep it here. Okay. What I do, I will take the first one. I am doing as before. So it becomes Z to the 3. Then I multiply Z to the 3 here. It becomes Z to the 4 minus, this is the crucial part, I Z to the 3. See, the coefficients now become complex. But the idea is the same. So I start as, oh, sorry, I have to change the signs as well. Okay, so now I add them. This one and that one are gone. But these two are similar because both are containing z cubed. So 2z cubed plus iz cubed. I cannot have 2z cubes when I bring things down. So it means that I have to factor 2z cubed out. So then it means that I would write 2 plus I z cubed, and then I will have 3z squared plus 2z plus 2. Okay? And now again, I have to divide this by z. So 2 plus I times z cubed divided by z. It becomes 2 plus I z squared. So this is what I have to transfer here. So this becomes plus 2 plus I z squared. Then I multiply the whole thing here. It becomes 2 plus I z cubed. I change the sign and put it here. So it becomes minus 2 plus I z cubed. Yes? I will multiply this by the next one. Let us just do it in a scratch paper. So 2 plus I z squared multiplied by minus I. So it becomes minus 2I minus I squared z squared. But minus I squared is 1, so it becomes 1 minus 2I z squared. So that is exactly that I have to put here, but with the opposite sign. So the sign would be minus 1 minus 2I z squared, and then I do the same thing. I add them. This one and that one are gone now. So if you can do it in your head better, otherwise you go to scratch paper. The coefficient here is 3. The coefficient here is minus 1 plus 2i. So it becomes 2 plus 2i. Yes? So it becomes 2 plus 2i z squared. And then I bring 2z and 2 down. I do the same process once more. So I divide this by that. It becomes 2 plus 2i z. And then I will take this one and multiply the whole package. So the first one becomes minus 2 plus 2i z squared. But let me just do this again in a scratch paper. So 2 plus 2i z multiplied by minus I. So it becomes minus 2i positive 2z. I change the sign and I put it here. So it becomes, if I change the sign, it becomes positive 2i negative 2z. And I add them again. You see? This is gone. And then if I add this 2 with that 2, it becomes just 2iz. And then I bring z2 down. I do once more. This 1 divided by z is 2i. So I put 2i here. And then I multiply 2i by z and change the sign. And I multiply 2i by minus I. It becomes positive 2, but I change the sign. You see? I also get 0 as predicted. But it means that at least it is good to see. If I wanted to follow the same old trick, this is why it's a level 3 problem. Because even if you succeed to do all this mess, then you will face this problem. I don't ask you this question in the exam, but I just want you to see that what is happening. If you just want to start immediately dividing, okay, it's not wrong. It was doable. We also got the remainder equal to 0. So everything is consistent, except for one practical thing. If I put this equal to 0, what happens? This gives me either this one is 0, I don't have any problem, and that's not a good information. I already knew about it. But the problem is that now I have to solve this horrible equation. So do you think that I am making the problem simpler? I would say that even though this is a third degree equation, because of the form, it is even harder than the original equation. I hope that you agree with me as well. So this is why you see that for solving this problem, if you really don't want to use the theorem that I mentioned it about, so you face this problem. So it means that you cannot solve the problem because what you can get is z equal to I, which is already given in the problem itself. Then you need to solve this problem. So here, the nature of the problem was somehow, even though I was able to reduce the degree by 1 unit, but I would say that this new problem is harder than even the original problem. Okay, so this I just want to give you as an extra piece of information. Don't worry about this solution. Or at least I hope that you understand. The only interesting part is that how you want to do it if complex numbers are also involved. So long division is also possible when you are doing it on the set of complex numbers. That is the only take-home lesson for you, and then you can immediately see it in front of your eyes that this usual method of doing things will face a very big problem here. Okay. Any questions here? I would say that I will go to the next problem. I want to give you a little bit of time to solve this problem yourself. This is also taken from Mathematics 5000. This is a level 3 problem there. And you have something similar in your book as well, okay? So I will stop this video and I want you to work on it for, I think 10 minutes is enough. Then I will come back and try to solve this problem for you, okay? Okay. I hope that at least you know what to do. Let me just highlight the points. I have a polynomial. You see again, I have the same problem. It's higher than 3. And I have provided one piece of information. I know that 1 plus I is a root to this polynomial. If I want to naively start by dividing this by z minus 1 plus I, then I will be in real trouble because even this number is bigger. And then at the end of the day, after all those efforts, I will not be able to solve the problem because then I will be left with a third degree polynomial equal to 0, which is probably for human brain is more or less equivalently hard. Okay, so what we do, you see that z 1 plus I is a root. Based on the previous theorem, the coefficients are real. I can conclude that 1 plus I bar, which is 1 minus I, is also a root. What is the next step? The next step is that, so P of z is divisible by z minus 1 plus I. P of z is divisible by z minus 1 minus I. So this means that P of z is divisible by the product by z minus 1 plus I times z minus 1 minus I. But what I need to do, I need to simplify this as much as possible. So what I do, I multiply this out. So this becomes equal to z squared minus 1 minus I times z minus 1 plus I times z plus 1 plus I times 1 minus I. Yes? So I am multiplying this here, I'm multiplying this here, then I multiply this here, multiply this there. And I will definitely simplify them. So this becomes z squared. Between these two, I factor a minus z out. From the first one, 1 minus I is left. From the second one, 1 plus I is left. And then I multiply them using the conjugate pattern, so it becomes 1 minus I squared. I can simplify it even more, so it becomes z squared. This one and that one are gone. This one and this one becomes 2, so it becomes minus 2z. And then if I ask you what that is, you would say it is 2. Yes? So this is also the first time that you are supposed to divide by a bigger expression. No problems. Okay, that's the idea is exactly the same. So let me make it smaller so that I can see. So what I do, I will take, by the way, I am skipping the first part. Okay, this is not very hard. Yeah, please do it yourself. You need to replace z everywhere with 1 plus I, and then hopefully you have enough experience how to calculate and show that this is indeed equal to 0. So I skipped the first one. Yeah, I want to do the second one. So for the second one, I will take z to the 4 minus 2z to the 3 plus z squared plus 2z minus 2, and then I divide this expression using the long division method. This is the first time that you are dividing by an expression with more than 2 terms. This is 3 terms. Okay, but the problem is that you can solve the problem as before. You divide z4 by the first term, so it becomes z squared. You multiply z squared there, change the sign. And then add them. When you add them, 2 of them are gone. And then with add them, it becomes minus z squared plus 2z minus 2. And then I do the division once more, so immediately you see that I get minus 1. I multiply minus 1, change the sign, it becomes positive z squared minus 2z minus, it becomes positive. And then immediately I get 0. So you see, even if it was easier, you had more terms, but the long division is just 2 steps. Okay? And then what happens, this means that P of z is equal to z squared minus 1 times z squared minus 2z plus 2. Yes? And if I put it equal to 0, then it means that z squared is 1. This means that z is plus or minus 1, so these are 2 roots. And then the other one, of course, you don't need to solve, yes, because you know that 2 roots are 1 plus I and 1 minus I. Definitely the answers are coming from here. And then if you don't believe it, you can just solve it, but this will not give you anything extra. So you just use ABC formula here, it becomes 2 plus or minus 4 minus 8 is minus 4 divided by 2. So it becomes 2 plus or minus 2i divided by 2, and it becomes 1 plus or minus I as we predicted. So the roots that we were not aware of were plus or minus 1. So you see, this method is actually extremely helpful if you want to solve a little bit higher level questions. Yes? And we can also, of course, you need to, of course, check that this one is easy. But you have enough experience. 1 plus I to the power of 4, you can write it as 1 plus I to power 2 and then to power 2 first. So this becomes just 2i to the power of 2 is minus 4. So these kinds of calculations are very easy when it comes here. Okay, so if you don't mind, let us end the meeting 15 minutes earlier so that Morten can also use the Aula for the test. Okay, so I will